This phase diagram, it just stays as H2O. I like to draw H2O like an oxygen atom with two little protons hanging out here at an angle that's almost tetrahedral, right? Because of bonding, and this is what I'm doing now as I'm teaching Chem 20A at the same time. And then the two hydrogen atoms are just donating their electrons. They're mixing it in with oxygen. And so here's my water molecule. It's plus at this end, it's negative at this end. So it's like a sphere that is a dipole. It's like a sphere with a positive charge on one side, +1, and a negative charge on the other side, -1. And so you can imagine when all the spheres come together that they might interact with each other in ways that are interesting, right? So, okay, so this is our water phase diagram. And so what I'm going to talk about today is how do we know what this phase diagram is? How do we read any one component phase diagram? And also, how do we take the combination statement of the first and second laws of thermodynamics, which I think is what you've been doing up to now, dynamics, to construct a one-component phase diagram. Okay? So, we need in our pocket a combined statement of the first and second laws of thermodynamics, which is a statement of the free energy. And so I have Gibbs free energy. So who's seen an equation for Gibbs free energy in a one-component system? Who's still kind of working through what their understanding is of Gibbs free energy in a one-component system? Okay, good. So I have three equations. For a differential, a small change in the free energy of a phase, in this case, and we'll talk about that. As you change either volume and pressure or entropy and temperature, sets of conjugate variables, and I have three statements. Are they all correct? No, just one is correct. Is it choice A? The change in Gibbs free energy is volume times the change in pressure minus temperature times the change in entropy. Is it B? The change in free energy is now the pressure, holding pressure constant, times the change in volume minus entropy times the change in temperature. Or is it 3? The change in free energy, this is Gibbs free energy. Is it volume, change in pressure, minus entropy, change in temperature? Who says it's A? Who says it's B? Who says it's C? Who's still not sure and working through it? Okay, good. Okay, it is indeed C. And let's talk about why. Okay, so now I have two plots kind of prepared for you, ready. Can everyone see these? Just want to make sure that the plot isn't in between the left and you like that? Okay, good. Okay, so here, okay, good. So we're looking at how this G changes differential as a function of some combination of volume, pressure, entropy, temperature, and calculus is a little funky, so we're not quite sure exactly how to do it yet. And I have two plots. I have this plot here, where I'm keeping one of these things constant, and I'm changing the Gibbs free energy with respect to one of these other things. Okay, and what's the Gibbs free energy doing as I'm changing that? And I have two options here, but it's doing the same basic thing in both cases. What's it doing? It's increasing, okay? So as I change one of these variables, the free energy is increasing. So what are the options for those variables? And which one is being held constant? What am I holding constant? Temperature? Okay, anyone have another idea? Pressure? Let's try to hold pressure constant, just for fun. Okay, so if we hold pressure constant, what's the change in pressure? 0, good, okay, so we can get rid of this. Okay, good, so if we hold pressure constant, the change in pressure is 0, this goes away, and we have dg is equal to minus s dt. So if we increase either of these, entropy, or increase temperature, what happens to Gibbs free energy? What happens, what does it do? It decreases. So is this constant pressure? No, it's not, because this is increasing. Okay. So what else can we hold constant? Temperature, okay? Or entropy, if we feel like it. We could choose either or. Okay, if we hold, well, S is just a constant here. We hold it constant. Well, we could still change the temperature. So I guess we do kind of have to hold the temperature constant. Okay, so if we hold the temperature constant, this is 0. Then as we change either volume or pressure, what happens to the Gibbs free energy? It goes up. Okay, so this one is definitely temperature constant. Okay? And by the same reasoning, this one is pressure constant. Okay, super. Okay, good. So we know that as we hold temperature constant, as we increase either volume or pressure, our Gibbs free energy is going to increase. All other things have been held constant. It's a one component system, so all other things are equal. Those words, all other things are equal, is, you know, if you're actually doing thermodynamics with pencil and paper and you have to write all of your little subscripts, that's what you're saying when you're doing calculus and holding everything else constant. Here, our Gibbs free energy, we're going to hold constant pressure. This goes away as we change entropy or as we change temperature. The Gibbs free energy, as we increase either of these, that Gibbs free energy is going to go down. And we're going to come back to these and start talking about which choice we like. Does it go down concave down, or does it go down concave up? That's going to be our next story. Okay, we have that in our pocket. That's a little bit of a review. I think, is it a review, or have you kind of worked through those Gibbs free energy curves? Have you worked through the Gibbs free energy curves, or is it still something you're grappling with? Working through, grappling. Okay, good. So it's a good review. Okay, great. So let's go to the easier part, and then we'll come back to the hard part. Okay, ta-da! One component phase diagram for water. How do we know this? How did we determine it? Yeah. Experimentally. Yeah, exactly. And we can do this experiment at home. We can take our coffee, assume that it's mostly water, and put it in the freezer for shaved ice coffee later in the weekend. Okay, so let's do that. Let's start here at room temperature. T room. And then we have some room pressure. Let's do 1 atmosphere. Okay? And we're here at room temperature. What's the stable phase of water? Liquid. Okay, good. So let's, and where's, if we raise the temperature at constant pressure, what happens to the water? Let's make the coffee. Let's put the water in the hot pot. Press the button so the temperature starts increasing. Just stays liquid the whole time? No, what happens? It boils at what temperature? Right. I hear 212 Fahrenheit. I hear 100 centigrade. Okay, Okay, that's good. I have 373 Kelvin. It doesn't matter right here, right? And this is the boiling point. So here, at this pressure, and let's do room temperature, let me make this a little bit more. Let's make room temperature a little bit more towards here. So this is T boil. This is T room. I'm going to call boiling 100 degrees Celsius. I'm going to call room 19 because it's cold in here. 19 degrees Celsius. Okay? What phase is water? Liquid. This whole area here is liquid. Anywhere as you increase the pressure, increase the temperature, decrease the temperature, it's liquid until you hit these lines, these two-phase coexistence lines. Okay, great. So here we boil. If we have our boiling water or water vapor, so this is vapor, which means that it's H2O molecules in a gas phase. Gaseous H2O. So it's these little dipoles, kind of much further apart with all their degrees of floating around. Okay, good. If we have vapor and we cool it down, what happens when we hit this point? It condenses. So this is condensation, vaporization, down here. Okay, now we're going to cool it down further. Okay, so I've made my coffee, boiled my water, steeped my coffee, and we're just assuming that it's pure water. We're really not worrying what happens when we mix all the coffee parts in there, and we're lowering the temperature. Then what happens? I'm putting it in my freezer. It cools down, stays liquid. Now I have a really good freezer because I love shaved ice, and at some temperature, it freezes. Freeze. Okay, what temperature is that? 0 degrees Celsius. Fabulous. Okay, great. And as I keep lowering the temperature, what phase do I have? Solid. One component, H2O, in this temperature and pressure regime can be either a solid, and then we're just going to call this ice 1. And there's a lot more ices way up at high pressures, but that's going to be out of scope. Although it is in scope. It's still one component, and you can still read off the behavior on the phase diagram. Okay, so solid, liquid, vapor, or gas. You can use either word in this case. Okay, great. So there's our phase diagram. Fabulous. And we did it experimentally. Okay, my background is in high pressure mineral physics. I study the properties of materials at high pressures, which means when I run an experiment by taking the material and smashing it between two diamonds are really hard, they're really transparent, so you can take a look and you can bring things up to really high pressure, which is how I know that ice has a whole phase diagram up here. In fact, if we took frozen ice and we just hold it at freezer temperatures and now start raising the pressure, when we're starting at room pressure, we go up, 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 up. We're going to get ice, and this gets really complicated. I don't even remember if it's 2 or 3. There's a whole zoology of more ice phases out there. Okay, they're fun to play with. And we're going to learn the tools, I know that you're doing this today and probably into next week, of being able to take any old phase diagram and being able to say something about the phases in a one component system. What can we say? We can say something about the phases volume per molecule or density, if you know the mass. So that's really useful, is Is it gonna sink or float? We can say something about its entropy. When we're saying something about entropy, what are we saying? What physical intuition do we have about entropy? What has more entropy, a liquid or a gas? Gas. Why? I heard more volume. Yeah, they have more degrees of freedom. Yeah, liquid, I mean, it can move in any direction, but the particles always are basically touching each other in a liquid. They're rolling around on each other. Okay, so that's a degree of freedom. You know, two water molecules, you know, kind of always in contact. And they could tumble, they could flow, they could be turbulent, but they're always moving. You separate them, they're not interacting anymore. Each of them has a lot of degrees of freedom because now they're uncoupled from each other. Once two particles are touching, they always have to stay touching. And they can do lots of interesting things if they're liquids that they can touch. Solid versus liquid, which one has higher entropy? Liquid, why? Yeah, the particles can move around more in different directions. Water. Oh, just for fun, let's talk about liquid water and liquid nitrogen, N2. Okay, so something that has approximately the same mass, approximately the same volume. Let's ignore temperature right now. So we're I want something that, okay, you're the chemist. I need a molecule that is the same, everything, the same volume as water, but non-polar, and also liquid.
Benzene?
Okay, benzene. Okay, we've got benzene, we've got water. Okay, and they both flow. Yeah, and let's just imagine that benzene is a sphere. It's about the same size as a water molecule. Maybe it's a little bigger, but okay, it's just non-polar. Wait, what's going to have more entropy, degrees of freedom? Benzene or what? Would we predict based on that? Benzene, why? Yeah, we know things about benzene. This is. I was going to say, if we can make a water molecule that is non-polar, for example, like water, one water molecule and another water molecule, they'll never be both the same side. I mean, they'll never have their, their pluses, pointing to each other. So there is a constraint that lowers the entropy for water. Okay. If there were no dipole, then it doesn't matter. It wouldn't matter if the water were in this direction or not. It would be an extra degree of freedom, and it would have higher entropy. So these details kind of start to matter for entropy. And if you think of entropy as degrees of freedom, it will help guide you around these systems. Okay, let's go back. Okay, great. So we know that this has low entropy, medium entropy, high entropy. As we go at constant pressure from low temperature to high temperature, we always cross from a low entropy phase. If we cross a phase boundary, we go into a higher entropy phase. When we cross a phase boundary, we go into a higher entropy phase. So that's just holding pressure constant. Now let's hold temperature constant, a freezing temperature, and go from really low pressure to really high pressure. Okay, so that's what I do. This is my experiment. And now we're going to do it kind of a little bit more out. So let's take this freezing point here and then bring it down to like vacuum pressure. What happens to solids in vacuum? well, you know, the surface of the solid sees nothing on the other side and definitely will want to join the nothing, right, to increase the entropy of the nothing, which will always lower the free energy. So there's always going to be some vaporization, some sublimation of any material, a solid, at zero pressure. There's no perfect vacuum. And so we're going to increase the pressure now. We still have a vapor. And then at one point, we cross this line. What happens at this line? We're turning from a vapor to a solid. Yeah, exactly. And that has a name. What's that called? Good, sublimation. Good. Okay, great. And then we're going to increase pressure more. And we are increasing it, room pressure, we have solid, and then we're going to increase it more, and then what happens? Yeah, we're crossing another phase boundary. As we increase the pressure on ice, solid, what happens to it? It melts. That's really weird. So we increase the pressure and we get a liquid. A little counterintuitive, but that's what our phase diagram tells us, and it is true. I mean, we increase the pressure more and we get another solid, you know, our high pressure forms of ice fill in. So don't worry, we're gonna get our solids back up there again, but not in this textbook level. Okay, great. Okay, so we're holding temperature constant. I mean, we're holding, temperature constant. And we're increasing pressure. Okay? So now we're going to know something about the volume of our gas with respect to our solid. Per mole or per molecule, what is more volumey? What has a larger volume, the gas or the solid? The gas, right? And as we go from here, from low pressure to high pressure, we go from high volume to low volume. Let's think in terms of density. What's density? It's mass per volume. I like density because we all know how to estimate, you know, the density of chalk is equal to, you know, 2 grams per cc. Density of water is equal to 1. This is our liquid water. Density of ice, what is it? It's about 1. Is it less dense or more dense than? Less dense. How do we know that ice is less dense than water? It floats. Great. Okay, good. So you're all empiricists. Whenever you get lost in thermodynamics, and you will, because it's really complicated, it's really mathematical, it's really difficult, remember that the whole thing was built up around our measurements, our observations, around our horse sets. For what's denser, what's less dense, what has more degrees of freedom, what has fewer degrees of freedom, what floats and what sinks. And so all of this math was built up to explain that, and a whole lot of other things, like you know, how an engine works, but that's a different kind of thermodynamics. Okay, great. So as we go from vapor to solid, we go from highest volume to medium volume, and then we go to liquid, which has lowest volume. V low, V medium, V high. Isn't that cool? I mean, within a gas, right, we have an equation of state. So we know how volume changes with pressure and temperature. PV equals RT. And by V, I mean molar volume. Solids, In this range, you can think of the volume and the entropy is more or less constant. But as you increase pressure at constant temperature, what happens to the volume? It decreases even a little bit. So even really hard materials, and I'm a high pressure physicist, so when I raise things to really high pressure, I mean, that's what we're measuring, is how much does a solid like ice compress? That's its compressibility. Good. As you increase temperature, what happens to the entropy? Increases, always. So if you calculate the entropy of an ideal gas, which I think you do in this class, what happens to that entropy as a function of temperature? Increases a lot, right? And we know that. So within each phase, it increases. And then when you cross a boundary, there's a jump. Great. Okay, let's do one more thing. Oh, any questions about this phase diagram? There's a lot of cute parts. There's this part where all the phases meet the middle. That's called the triple point. If you were to bring things to this pressure, which is really low, like this is 1 atmosphere and this is like 0.01 atmosphere, low pressure, and if you were bringing to the temperature to this, which is just a teeny bit above 0 degrees, it's like 0.1 or something. It was on my notes that I left upstairs. And you held water there, you would have all 3 phases, a vapor phase, a liquid phase, and a solid phase in equilibrium together. This one, it ends. See how that line ends? This line goes up forever. This line ends. That's called a critical point. And what do we have out here? Something really weird that is correlating over long distances, and all sorts of wonderful things happen in that critical point. But we're not going to talk about that, because I want to now go to, we're going to hold temperature constant and ask about the Gibbs free energy now. These are our tools, our quantitative tools for building this diagram. So with temperature constant, what are we asking about Gibbs free energy doing? Increasing as a function of pressure. Okay, so here is a plot of the change in Gibbs free energy is equal to V dP. What's the slope of this curve? dG dP. What's dG dP? Volume. There's our volume. Let's just take some pressure, we'll call it atmospheric pressure, and we'll just look at the slope right there. Cute, that's the volume right there. Isn't that cool? As we increase pressure, what happens to the volume? The volume. We're increasing pressure, what happens to the volume of something? Decreases. Is that always true at constant temperature and everything else held constant? Yes. Everything else held constant. You increase the pressure on something, the volume always goes down. You can hold your horse sense to that. I mean, there's caveats. Everything else is constant. Constant temperature, constant chemistry. You're looking at the three-dimensional volume, not stretching in one dimension. I mean, all of these things. So you can always be sure that as you're increasing pressure, volume is decreasing. So which curve is correct? The one where the slope is getting lower with pressure, or the one where the slope is getting higher with pressure? Yep, the first one, that lower slope. Good. Now you know G versus P without having to memorize anything, because you understand a water phase diagram because you have experience with it, and then you can tease apart what happens at constant temperature and ask what happens to this Gibbs free energy as a function of pressure. Isn't that cool? And you're writing this for like one of the phases. Let's just write it for water. So water, the volume of water, or 1 over the density, the entropy of water, so this is liquid H2. Okay, great. Awesome, good. I have a meeting to go to. So your TA is gonna finish up by doing the next